All right, so welcome to our last class meeting. Today's plan is to just finish up the dot and cross products. We're not going to cover equations of lines and planes. That was on here as a kind of optional topic. Um, just trying to shoehorn that in during finals week. And I didn't think it would be fair to put up another homework during finals week. Also, you've already got enough going on. So the homework from 12.1 to 12.4 that's been up for a few weeks now is due on Friday, so don't forget about that, but no additional homework on top of that. And then this Wednesday from 1 to 3, an optional review session. So again, that's just because we kind of have to do something during our during our assigned class time. So I'll treat that more like office hours. If anybody wants to pop in, ask any questions, feel free to. And then this week, the final exam has been posted since Friday. It's been available. It's to be taken on WebAssign using Examity, same setup as the unit exams. Sample exam has been available for a while now. You can use a formula sheet, just a standard size piece of paper front and back. You can put formulas, notes, anything like that you want on it. And as I mentioned before, definitely do not wait until the last day or two to take the exam in case something goes wrong. So I would recommend taking it Wednesday at the latest. And then if something goes wrong, there's plenty of time to work out a solution. Remember, the exam is due Friday the 10th at just before midnight. So make sure that you leave yourself a buffer just in case something happens. So with that being said, are there any questions uh, about anything related to either what we talked about last time or to the exam? Okay, so just to quickly recall some information about the dot product. Remember, the dot product u dot v is just the kind of component-wise multiplication, but then we add together. So we don't get a new vector out of u dot v. We get a scalar, we get a real number. There's not really a sense in which we would multiply components together and end up with a new vector, where we get like the first component being the product of the first components of the two inputs, and second the product of the seconds, and third product of the thirds. There's not really that kind of a sense. But the dot product, we get a scalar out. U dot v is this. This is sometimes called the scalar product, and we mentioned an important theorem that we're going to come back to today, that u dot v is length u times length v times the cosine of theta. And we said, as a corollary, if two vectors are orthogonal, if they meet at right angles, or we can roughly say if they're perpendicular, or they're perpendicular or orthogonal, if and only if their dot product is 0. Okay, so moving on to the cross product. We mentioned last time, and we spent a good bit of time dealing with the fact that the cross product is defined in this kind of funky way. It's you look at this and you say, who the heck thought this up, right? It doesn't look like there's any rhyme or reason to it. We did note that there was some rhyme or reason, and we said that basically the idea is, or let's say one memory device, if you want to think of it that way. Oops. So if u cross v, if u is u1, u2, u3, v is v1, v2, v3, we start by putting I hat, j hat, and k hat in the top row of a 3x3 matrix. And then we have u1, u2, u3, and v1, v2, v3. And we want to take this thing called the determinant. And we talked about this idea of cofactor expansion, the, in some sense, like more official way to do it. Or there's the shortcut way. We copy over the first two columns. And then we look at diagonals. These three diagonals come in with plus, and these three with minus. So we just multiply everything along the diagonals. The kind of top left to bottom right diagonals for I, J, and K get pluses. So we'd have, for instance, plus U2 V3 I hat would be one of our bits that we get out of this. And then the off diagonals come in with minuses. Okay, so that's, I think, about where we got last time. So a property of the cross product is that if we take a vector cross itself, we get 0. And why is that? Well, if we look at the symmetry up here, like U2 V3 minus U3 V2, if the U's and V's are all the same, then we just have U2 U3 minus U3 U2. Of course, that's 0. So the cross product of a vector with itself is 0. Remember that the, oops, I didn't copy over the properties, but remember that the dot product of a vector with itself, well, we can see pretty easily from here, cos of 0 is 1. We would just have the length squared. The dot product of a vector with itself is the square of its length. The cross product of a vector with itself is 0. And importantly, remember that the cross product is a vector. So the dot product is a scalar. It's a real number. It's sometimes called the scalar product. And the cross product is a vector. So when we say that the cross product of a vector with itself is 0, what we really mean is the 0 vector, 0, 0, 0. We saw that the dot product was commutative. U dot V was V dot U, exactly the same, just based on the commutativity of integer or real number multiplication. The cross product, well, we see that these components are sign dependent, right? There's a minus sign. So if I switch the U's and the V's, my first term swaps with the second term, and then I end up with the negative of what I started with. So the cross product is kind of like anti-commutative. It commutes, but pops out a negative sign. Now we can ask, okay, I have the cross product. The cross product is a vector. It's this vector. As a vector, it has a length, right? It has a magnitude and it has a direction. And what is the length or the magnitude of the cross product? Well, if we consider two vectors, let's say vector U and vector V, and we consider the parallelogram that is made by something similar to doing a U plus V kind of construction, I have this parallelogram with an enclosed 2D area. So I have an area here. This area turns out to be the magnitude of U cross V. And of course, because we're taking a magnitude, it doesn't really matter if it's U cross V or V cross U. So it's the area of this parallelogram. We have a similar theorem that corresponds to the dot product one. The dot product of U and V was length U, length V cos theta. We have a similar, I have a typo here. Let me fix that really quickly. Quite important. There we go. Thought something didn't quite look right there. If we take the cross product of two vectors, its magnitude is a scalar. And it turns out that it can be written as length U, length V, sine theta. So length U, length V cos theta is the dot product of the two vectors. Length U, length V sine theta is the magnitude of the cross product of the two vectors. And a corollary of this is that two vectors are parallel, they have the same direction, if and only if their cross product is zero. They're parallel if the angle between them is zero, and of course, sine of zero is zero. So two vectors are parallel if and only if their cross product is the zero vector, which is equivalent to saying that the magnitude of their cross product is zero. Two vectors are orthogonal or perpendicular if and only if their dot product is the zero number, the zero scalar. So kind of an interesting thing about dot and cross products. I mean, this seems to be just a motley bunch of ideas kind of thrown together. Like, why would we ever define cross product this way? It seems kind of nonsense. I mean, I guess there is this area of the parallelogram thing. Why would we define the dot product this way? Like, okay, maybe there's some interesting stuff related to some future ideas in linear algebra of inner products and so on. But again, it seems like kind of a silly thing to do. I think the one step underlying idea is seen in these theorems that the dot product looks like the cosine of the angle between the vectors, and the magnitude of the cross product looks like the sine of the angle between the two vectors. So kind of like roughly speaking here, we don't often say roughly speaking in math, but here we will. The dot product in some sense is kind of a representation of something like how parallel two vectors are, right? If we have two vectors that are perpendicular, like kind of not at all parallel, like as much not parallel as you can get, their dot product is zero, and their dot product is maximized. It's as large as it gets for the same two vectors if we're rotating them. The dot product gets as large as it can when they're parallel, when the angle between them is zero, when the cosine is one. That's when the cosine is maximized at theta equals zero, when they're pointing in the same direction. So the dot product is kind of like how parallel they are. If they're not parallel at all, if they're perpendicular, the dot product is zero. If they're very close to parallel or just parallel, their dot product is very large, relatively speaking. And the cross product is kind of, in a rough sense, a representation of how perpendicular two vectors are. If the vectors are parallel, kind of like as non-perpendicular as you can get, roughly speaking, their cross product is going to be zero. The zero vector, or the length of the cross product, is going to be zero. So for like very non-perpendicular vectors that are parallel, the cross product is zero. And for perpendicular vectors where they meet at 90-degree angles, that's when the sine of theta is one. That's when the magnitude of the cross product is maximized. That's when that cross product vector is as large as it gets. So in kind of some kind of sense, the dot product and cross product kind of trade off parallelism and perpendicularity. I guess I don't know if that's maybe those are two good two correct words. I'm not exactly sure, but they kind of trade off the idea of how parallel and how perpendicular a vector is. Sorry, two vectors are. A vector is with another vector. Dot products are important in things like projections as well. So if I have two vectors and I want to project this vector, say u, onto the vector v, in other words, I want to imagine like a flashlight or a sun ray or something like that coming down perpendicular to v. What would the shadow that u would cast on v look like? It would look like this. If u is like nearly perpendicular to v, it casts a very short shadow. If u is very nearly parallel to v, it casts the longest shadow that it can. So that's another example. We obviously didn't talk about linear projections or any of that, but that would be an example where you could kind of see this in action. Okay, so let's do a couple examples, a couple of calculation-based examples. So here we have three examples, and we want to, for these following three vectors, compute the dot product and decide whether the vectors are perpendicular, orthogonal, parallel, or neither. And remember, I'll just copy it down here. I'm gonna just pop it over here. So remember, for orthogonal, we're looking for whether the dot product is zero. So u dot v. Here I have two-dimensional vectors. That's perfectly fine. We can do a dot product with 2 or 3-dimensional vectors, or 4 or 5, that for that matter, but 2 dimensions works fine. I take my first components, I multiply them together. To that, I add the product of the second components. Why do I choose so many 4s in my examples whenever they're so hard for me to write? And I see I get negative 28 plus 28 is 0. Well, since their dot product is 0, they are perpendicular. They are orthogonal. If I look at the next example, again, I can compute the dot product to see if they're orthogonal. Three times negative 6, multiply the first components. To that, I add the product of the second components. What's that? 7 times negative 14. And to that, I add the product of the third components, negative 6 times 12. So this is negative 18 minus, what's that, 84, minus 90, minus 72. And what does this give me? 72 and 18 is 90. So is that negative 174? I think if I did my arithmetic right. But the important thing is that this is not 0. So these are not perpendicular. This kind of upside down capital T looking thing is the symbol for perpendicular. So we'll just write it this way. These are not perpendicular. But I suppose I still have two possibilities. They could be parallel, or they could be neither perpendicular nor parallel. They can meet at some angle that is not 0 or 180, but is also not 90. How do I tell if two vectors are parallel? How do I tell if two vectors have the same direction, but just a different magnitude, or possibly exactly the opposite direction with a different magnitude? Well, remember, if I keep or for me to keep the direction the same and change the magnitude, that's when I multiply it by a scalar. So if this was vector A and this was vector B, if I can multiply one of the vectors by a real number and get the other vector, then the two vectors are parallel. And they're parallel and pointing in the same direction if that real number is positive, pointing in the opposite direction if it's negative. So let me do this on a separate line here, not try to squeeze it in. So what am I asking here now? So these are not perpendicular. Are they parallel? In other words, is it true that U equals KV? Or vice versa, that V equals KU? Well, for U equal to KV, for U to be equal to KV, that means U1 equals KV1 and U2 equals KV2 and U3 equals KV3. v3. So we just have to solve one equation for what k has to be, and then see if it works for the other two. If it does, then they're parallel. If it does not, if there's there's always going to be an answer for k for one of these equations, but if it doesn't satisfy all three at the same time, then they're not parallel. So 3 equals k times -6, k equals -1/2 is 7, -1/2 times -14. Yes. And is -6, -1/2 times 12. Yes. So these are parallel. And then for my third example down here, are these perpendicular or orthogonal? I think we usually use perpendicular in 2D and kind of orthogonal otherwise, but I'm being a little, I'm not being super careful with those two words here. Are these perpendicular? Are they orthogonal? Is their dot product 0? So again, computing the dot product, I just multiply the first components. 4 times 3 is 12. To that, I add the product of the second components. -8 times 2 is -16. And to that, I add the product of the third components. 1 times 5 is 5. 17 minus 16 is 1, which is not 0. U and V are not perpendicular for this U and V. Are they parallel? Well, I'd have 4 times what? 3/4 gives me 3. That's the relation. I would need a constant multiple of 3/4 to satisfy the first component, the constraint on the first components. But of course, -8 times 3/4 is what? -6, which is not 2, the second component on the right side. So -8 multiplied by that same constant that made the first components work out okay does not give us our second component. The second constraint is not satisfied for that same constant. These are not parallel. I think usually we write something like this for parallel, but then if you put it across through that, it's, I don't know, for me, the kind of not parallel sign actually just looks a little more confusing than just saying not parallel. The not perpendicular sign is kind of obvious that it's a perpendicular with a slash through it, but the not parallel doesn't look as clean in my opinion. So these are two vectors that are not perpendicular, they're not parallel, they're neither. That's a perfectly fine option too, right? They just meet an angle that's not 0 degrees or 180 and not 90. So, I mean, if we just pick two random vectors, they're almost certainly going to be neither perpendicular nor parallel. Any questions so far? Okay, so let's do an example of cross product then. We're going to compute the cross product and verify that the resulting vector, remember that the cross product is a vector. We're going to verify that the resulting vector is perpendicular or orthogonal to both original vectors. This was a property we mentioned last time. So I'd like to start by computing U cross V, the cross product. I could just plug into the formula up above, but I think it's a good practice to just go through this a couple of times. This matrix determinant kind of method. Remember that it does matter which one comes first. U cross V is negative V cross U, so we got to be careful to get the U in the second row and the V in the third row. So it is important which order. So what is it? 3, 2, -5, and 2, -6, 4. That's what I want to take the determinant of. And remember, instead of doing that whole like cofactor expansion stuff that we talked about, that's nice and all, but it's kind of a pain. It's cumbersome. I have this little trick that works for 3x3s. I copy the first two columns over, and then here I think I'm gonna circle the entries, because if I cross them, I'll probably end up getting the numbers wrong or something. So this comes in with a positive. This comes in with a positive. And this with a positive. Let me just write these three down before I go the other direction. So I have I hat is multiplied by positive 2 times 4 is 8. Plus j hat is multiplied by positive -5 times 2, -10. We know we're going to get another contribution for each of these when we go the other direction, so I'm going to leave a little bit of space. And k hat is multiplied by positive 3 times -6 is -18. Okay. Now I'll go the other direction. Here I have k hat getting multiplied by -2 times 2, -4. I've got I hat getting multiplied by -5 times -6, or -30. That's for I. And j hat getting multiplied by -3 times 4, -12. And fingers crossed this came out right. I get I hat, or let's write it this way. 8 minus 30 is -22 I hat, minus 22 j hat, and minus 22 k hat. Or I could write that as -22, -22, -22. Or sometimes we just call the vector 1, 1, 1 the identity vector. We could call it -22 times the identity, like that. Sometimes it's I for identity vector or identity matrix. Sometimes it's like a 1 like this with a vector symbol over it. So that is our cross product. Obviously, I tried to make it easy on myself to check and to do the next couple of steps. We also want to verify that this vector, -22, -22, -22, is indeed perpendicular to both of these original u and v vectors. That was one of the characteristics of the cross product that we had mentioned last time. Let's verify it in this example. In other words, what I want to do is I want to take the dot product of this vector with u and show that that's 0. And I want to take the dot product of this vector with v and show that that's 0. So let's just call this, I don't know, let's call this W. W is u cross v. So what is W dot u? Well, W dot u is -22 times the first component of u, 3, plus -22 times the second component of u, 2, plus -22 times the third component of u, -5. We see that a -22 factors out, and we're just left with 3 plus 2 minus 5, really just the sum of the components of the u vector. 5 minus 5 is 0. It is 0. The dot product of this new vector, the cross product, with u gives me 0. This cross product vector is indeed orthogonal to U. U cross V, this vector is indeed orthogonal to the vector U. We could do the same thing with V. We really kind of see the pattern that because our cross product ended up being the same number 3 times when we dot it against V, the only way we're going to get 0 is if the sum of V's components are 0. And we could pretty easily see that that is also the case. 6 minus 6 gives me 0. So by a similar calculation, this new vector W, this U cross V, this vector, is again indeed perpendicular or orthogonal to the vector V by a similar calculation. Instead of 3, 2, negative 5, we would get 2 minus 6, 4. In these brackets added together, they would add to 0. Are there any questions on anything that we discussed today? Anything about the exam? Anything at all?